Hi, in this video we're going to talk some more about limits involving infinity, but we're going to discuss more of the formal details, so definitions and theorems related to limits involving infinity. Okay, so here on the screen you see a couple of different definitions for limits involving infinity, and these are not necessarily ones you need to memorize and be able to write down. But there are a few key things that you should at least understand and be able to answer conceptually about these two definitions. All right, so I'm just going to highlight and annotate what's written here on the screen a little bit so we can focus on a couple of things. So this first one is a limit where we are letting x approach infinity and the outputs of the function are approaching this value L, which is a real number. And so in this definition, I want to focus on a couple of important similarities and differences between the different definitions of limit that we had earlier. So when we looked at definitions of limit earlier, we were letting x approach a number and the outputs, f of x, were also approaching a number. All right, so we should expect that the stuff about the outputs of the function are going to be the same in this definition as we had in the previous definitions, right, where we talked about the outputs approaching a number, L. So notice that at the beginning here, we have this value epsilon, which is used to describe a distance in the direction of the y values, the outputs around L, so that part is the same. We also have this part here that should look familiar to you. The absolute value of f of x minus L is less than epsilon. But there are a couple of other important differences, and so you should understand that there are going to be differences in a couple places and why those differences are there and why what's stated here would make sense. All right, so the big deal difference about the definition of limit we're talking about here is that x is not getting close to something, x is getting far away from everything. So instead of talking about distances getting small, what we're really talking about here in this definition is distances getting bigger. All right, so this definition here says that we can find a real number m, so that whenever x is in the domain of the function and x is bigger or far away from everything, we're guaranteed that the distance between f of x and L is small. So f of x is close to L. All right, so the big deal difference here is that our x values are getting big. So we've got this greater than inequality involved when we're talking about x's, and we have some number m so that whenever x is bigger than that, we've got the outputs doing what we expect here for the limit. All right, and then I want to contrast that a little bit with the next one. So in this next definition, x is approaching a real number, and the y values in this case are what are approaching infinity. So conceptually, we'd be talking about that in terms of the y values getting big, the f of x, or the outputs getting big or far away. All right, so what we should expect in this definition is that the stuff about x is similar to what we had before in our epsilon delta definition of limit, but the stuff about the outputs, the f of x, is what's going to be different. Okay, so stuff about the outputs for every real number m, that's going to be about outputs, and that's different than before. We can find a positive real number delta. That part is the same as we had when we talked about the limit as x approaches c. So that whenever x is in the domain, and here this is the same, this is when x is close to c, within delta units of c. And what's different, again, is about the outputs, that the outputs are getting big or far away. Okay, so these are just really two different definitions. One, when x is approaching a real number, that's our second one here, and the y values, the outputs are getting big or far away, and then switched around for the other definition. But you should realize that if we really wanted to be complete, that we would actually need to state several other definitions. And so we would need a different definition for what happens when x approaches negative infinity. In that case, you would want x to be large in size, so far away, but in the negative direction. So we would have some different inequalities in that. We would have a different definition when the outputs are approaching negative infinity, again, large in size, but in the negative direction, so our inequalities would be a little bit different. We would have some different definitions if we wanted to combine, where we have both x and y getting larger without bound. So in the two definitions that are here, only one or the other of the inputs or outputs are getting larger without bound, but we would have a definition that would involve that. We could have definitions where we might have x approaches positive infinity and the outputs approach negative infinities. We'd have different inequalities on that. All kinds of different combinations of these would require technically different definitions. And then if we wanted to be really especially thorough, we could also consider writing all those definitions when instead of a two-sided limit for x approaching c from both sides, we might let x approach c from only the right or x approach c from only the left separately. So a whole bunch more definitions if we wanted to be really complete and think about all those. So you don't need to write all them down. You don't need to memorize them. But what I do want you to understand is that if you have a variable getting large, the things that I've highlighted here, if you have a variable getting large, x getting large, what that means for the inequality, that in the definition you're going to have an inequality where x is greater than something. Or if you have the outputs getting large, then in the definition you're going to have an inequality that's about the outputs getting greater than something. And the rest of the definition essentially is pretty much the same, but just kind of what would be different if you have these sort of different aspects for the definition here. Okay, so similar to the fact that there are many, many different kinds of definitions, and we're not going to write down all of them, but you could if you really wanted to. Same with theorems. So there are many, many different kinds of theorems that we could state about limits involving infinity. Our textbook does not state all of them. And we're not going to state all of them here either in our notes, but we're going to just state a few and kind of get the main idea. So if you think back to theorems that we had about ordinary limits, limits as x approaches a number and the outputs y also approaches a number, we started with some theorems about basic functions. And so let's just think about that a little bit here, some basic functions that we would like to have limits of, and then we could state some theorems about combining functions to combine those basic functions. So the most basic function that we started with when we started with theorems about basic functions was just the constant function, where the outputs of the function are some constant for all values of x. And so if I think about that function as x approaches infinity of that function and limit as x approaches negative infinity of that function. And so you should be able to think about this. The theorem would actually prove it using the epsilon m definition of limit. But you should be able to think about this if you just think about the graph of the function. If the function is just a constant function, then as x gets large in the positive direction or large in size but the negative direction, the outputs of that function are just going to be approaching k, whatever that constant is, in either direction. So an actual proof of that would require using that epsilon m definition, but you should be able to at least conceptually understand why that limit is what it is. All right, let me just write down one other sort of basic function. This is one that has several interesting limits, this reciprocal function. And before I write down some limits here, let's just draw a picture of that graph. So there are really four limits for this function that are worth thinking about. What happens as x approaches infinity and negative infinity, but then also when x approaches 0 from the right and the left, and what happens to the y values. So there are really four limits involving infinity that are important for this function. I'll just write them all down here. As x approaches positive infinity, you should be able to see that the outputs of that function approach 0. The graph is not a proof. A proof would involve the epsilon m definition. And it's not a hard proof. Our textbook, in fact, might do that proof. I don't know, but it's not hard to do. As x approaches negative infinity, if you just look at the graph, you should understand why this limit is what it is. The values, output values of the function get closer and closer and closer to that horizontal asymptote on the left end of the graph. And then I also have some important limits as x approaches 0 from the right. The outputs of the function approach positive infinity, and as x approaches 0 from the left, those outputs approach negative infinity. And that should help you understand that as x approaches 0, the function 1 over x, that limit does not exist because the two sides are different. Okay, and just like we did before, you could have all kinds of basic functions that you can prove things about limits with. Again, looking at the graph is not a proof. Epsilon m definition would be used to prove these kinds of things, but we're not going to go through those proofs here. You might do that in an advanced calculus class or something like that. But the idea is that you can prove all of these. And then the other important idea is that once you have some sort of basic functions, you can prove some theorems about combining functions. And our textbook states some of these. So for example, if I know that the limit as x approaches infinity of one function is one real number, we'll call that L. And I know that the limit as x approaches infinity of some other function, let's call that g of x, is some other number, let's call that m. Then I can combine functions in lots of different ways: addition, subtraction, multiplication, lots of different ways that we did that. I'll just do addition here. So limit as x approaches infinity of f of x plus g of x. That limit is what you would hope it is, L plus m. Just writing it down isn't a proof of that. I could use the epsilon m definition to actually prove that. But all kinds of different theorems here about combining functions. Here I did addition, but similarly you can do multiplication, division, subtraction, composition. You can also think about things like there is a sandwich theorem. Our textbook does not talk about sandwich theorem for limits involving infinity, but I'll go ahead and write that down here. Okay, so I have written down sandwich theorem here. There are a whole bunch more theorems that extend the theorems that we talked about before. So you can look in some other source, or you can ask me if you'd like a more detailed list of some theorems about combining functions or other theorems involving infinity. But what you will most often use in your homework is ideas concerning basic functions and algebra of infinity. All right, so I want to highlight a couple of things here. I don't want you to memorize these necessarily. I just want you to learn to think about these conceptually. One thing I want to emphasize is that infinity and negative infinity are not numbers. So we really can't define things like adding, subtracting, multiplying, and dividing them. But we often use some ideas, and this first one actually is the idea about combining functions using addition when the outputs approach infinity. So the idea here is that if I have some function, say f of x, that's approaching infinity, and I add that to another function, say g of x, that's approaching infinity, and those two functions are added together, I get a resulting function that also approaches infinity, right? So the idea here is that I don't really have addition for infinity plus infinity, but the idea is that something that's getting larger and larger without bound added to something that's also getting larger and larger without bound will still result in something that gets larger without bound. All right, and so there are many things on here similar to that. I just want you to kind of look at some of those. I'm just going to focus on a couple of them. If I have a negative number times something that is headed in the negative direction and getting larger without bound, should be able to understand that a negative times a negative is positive, and so that's why we have positive here, but the size would be getting larger without bound. All right, so lots of different things here to just kind of think through why these different things would be true. There is a warning here. You do have to be careful. There are some things called indeterminate forms, which you will study in some later study of limits in Calculus 2 at JCCC. Indeterminate forms, right? The important thing to understand for now about those is that you cannot assume that usual rules of arithmetic extend to these forms in this box. So these limits could be anything. If I have a function that approaches positive infinity and that's added to another function that approaches negative infinity and I add them together, it's possible that the result might approach positive infinity, or it could approach negative infinity, or it could approach some number, or that limit could maybe even not exist. So the key thing to understand is that those limits could be anything, and just thinking through large in size is not adequate to think about that. So you must investigate further. What are some ways you can do that without theorems? You could use a table or a graph for now. Later you'll learn some more theorems that might help with some of these limit forms. But for right now, the key thing to understand is that for some operations, like that are up above here where it says algebra of infinity, something getting large plus something getting large continues to get large. But if I'm thinking about one of them approaching positive infinity and the other approaching negative infinity, we don't know what that limit might be, and we have to investigate some other way. All right, so besides being able to combine functions, I've got here some useful limits to know. All right, and so most of these I tend to think about in terms of the graph of the function. So this first one we actually already talked about when I talked about constant function, that if you just think about the graph of the constant function, f of x equals k, when x gets large without bound in the positive direction or negative direction, those function outputs just stay k. 4, 5, and 6 are about the reciprocal function that we already talked about. And again, I really just talked about that from thinking about the graph, what x and y are approaching as we approach those asymptotes in those 4 different places. 2 and 3 talk about power functions, so x to a constant power. And so just kind of thinking about that, this first one, there's a lot of different kinds of graphs. So for example, f of x equals x squared is one kind of graph. We're really talking about the right-hand side of the graph here. F of x equals x cubed is another kind of function you might think about. F of x equals x to the 1/2. I'm going to put that over here to the left. Square root function is another graph you might think about. So on all of those, as x gets large, the y value continues to get larger, provided that the exponent is greater than 0. All right, so 3 different kinds of graphs there, but I want to use those 3 graphs to emphasize that as x approaches negative infinity, a power function, that depends on the exponent, but I would encourage you to just think about the graph of the function. So on these 3 graphs up above, on the f of x equals x squared graph that I drew, as x approaches negative infinity, y is approaching positive infinity. Y is getting larger without bound. On the f of x equals x cubed function, as x approaches negative infinity, y is approaching negative infinity. And on the f of x equals square root of x function, or x to the 1/2 function, x cannot actually approach negative infinity on that graph because the domain of the function does not go left of 0. So just kind of as a point of contrast, that it's easy to think about functions if you know you have a power function with an exponent greater than 0 on the right side of the graph, but the left end behavior is a little bit more complicated. So 7 talks about the limit as x approaches positive or negative infinity of the sine function. And so if you just think about the graph of the sine function, as you go further and further out to the right, that function just continues to oscillate between +1 and -1 and every value in between. And so those y values on the right side do not get larger without bound. They do not approach negative infinity. And they also do not approach a number, L. They continue to hit every number between +1 and -1 over and over and over again. So those limits do not exist on the right-hand side and on the left side of that sine function. And also that would be similar for all the other trig functions, because those functions are periodic and they repeat over and over and over again. They don't have any of these consistent behaviors. So for all of those limits do not exist as x approaches positive or negative infinity. All right, in the next column here are some basic functions you probably should know the graph of, hopefully you do, the e to the x function. On the right-hand side of the graph, those y values are approaching positive infinity, going up without bound. And on the left side of the graph, as x approaches negative infinity, those y values are approaching 0 on that horizontal asymptote. If you think about the inverse function for that, so if you don't remember what the graph of the ln function looks like, you can think about the e to the x graph and then just think about the inverse function, so flipping that across the line y equals x. So the ln function has a vertical asymptote at x equals 0. As x approaches 0 from the right, the outputs of the ln function go down, approach negative infinity. And as x approaches positive infinity, the outputs of that ln function approach positive infinity. They grow slowly. The y grows slowly over there, but it does continue to grow and get larger and larger and larger without bound. Whatever biggest y value you can think of, if you go far enough out on the graph, that y value will get larger and larger and larger. All right, this number 12 is really something about combining functions. If I know that I have a function whose outputs approach positive infinity, as x approaches infinity, then the reciprocal of that will approach 0. And then 13 is just kind of a cautionary tale, similar to what we saw on this reciprocal function. If I know that I have a function whose outputs approach 0, you need to think carefully about that reciprocal function. It's possible that this limit may not exist, or it's possible that this limit might be positive infinity, or it's possible that that limit might be negative infinity. Essentially, you need to think about which side of 0 the function approaches 0 from, whether the function outputs are a little bit smaller than 0, so negative, a little bit larger than 0, so positive, equal to 0, or different from different sides. So you need to think a little bit more carefully about that. And again, investigate using a table or a graph if you are not sure. Okay, next video has a bunch of examples in it of combining some of these ideas to find some limits of some actual functions.